Yeah, good evening. Can you hear me? Am I audible? Hello, am I audible? Okay, thank you. So let's start today's session. So today, the last week you guys have gone through the concepts on constitutive relation or Hooke's law in specific. So you have seen the equations where how the stress and strain are related, and then somewhat you studied about the thermal stresses also, and majorly you studied the Hooke's law, how uh, they are related, and how we can write it in for a two-dimension case, or how we can write it for three-dimension case, and then how many constants are there, then what is the generalized Hooke's law. Okay, so then how many uh, coefficients or the components of the elasticity matrix or tensor comes. So that you have done this and this week. So we'll solve some questions in this session on constitutive relation mostly. Okay, so that we understand how if stress is given we can find strain, or if strain is given we can find stress. Okay, so we'll start with that only in this week. Then next week I'll take some problem on thermal loading. I have given this time you guys also go through only this thing, the stress strain relationship. Next week we can solve some problems on thermal loading and some other concepts. Okay, so let's start. So the first problem for today's session I have taken. So in this problem, a strain tensor is given. Okay, so basically a strain tensor is being given in this form, and it is asked to find the stress tensor. Okay, so it has been asked to find stress tensor, so that the Young's modulus and shear modulus are given as this. Okay, so we need to find the stress tensor correspondingly. Okay, so first we'll go through the equation, how to uh, get the stress tensor using the Hooke's law, three-dimensional Hooke's law, and then we'll see like how to solve it. Okay, so okay, I'll solve it here itself. Okay, so I'll take the strain tensor from here. And then we'll work with this. Okay, so we have the strain tensor. Now let's first rewind the different relationships for the three-dimensional Hooke's law. So our Hooke's law, so it is defined like, if you want to find epsilon xx, how we find 1 upon e sigma xx minus nu time sigma yy plus sigma zz. Okay, this is sigma epsilon xx. Then we have epsilon yy, 1 upon e sigma yy minus nu sigma xx plus sigma zz, and then epsilon zz will be 1 upon e sigma zz minus nu sigma xx plus sigma yy. Okay, so these are the strain relationship where strain and stress are in coordinate direction, normal direction. And then we have the shear components. So these are normal strains. So shear strain components are, we have gamma xy is equals to tau xy by g. Okay, then we have gamma yz, that is tau yz by g, and then we have gamma xz is equals to tau xz by g. Okay, and G and E is given in the question. Okay, we mind that G and E is given. So but for finding the shear strains we can directly use the G, that is fine, but when we need to find the normal strains we need Poisson's ratio also, nu. Okay, we need that nu also. So now question comes, how to find the nu. Okay, so let's see. So you have gone through, so now our thing is first finding the Poisson's ratio. Okay, this nu. So you know the relationship between G and E. So here G is nothing but E upon 2 1 plus nu. This is the relationship between G and E, and we know both G and E. We can find from this relation, that is 1 plus nu will be E upon 2G. So basically nu will be E upon 2G minus 1. This will be the relationship for nu. Sorry. Correct. Okay, so from here we have to find the nu. So I'll request you guys also to find this value. We know what is E, we know what is G. It is 207 and this is 80 minus 1. I think that is the value. Yeah, 207 okay. So this will be what, with 2 multiplied here, I forgot that 2, so it will be okay, no issue. it's fine. Okay, so we can find this by dividing it by 2, and that is this way. Okay, VD minus 1, and subsequently we can will have this minus 1, and this will be 1.2. So something this minus 1. So as you can see, I'll take this approximately as 0.3. Okay, it is coming 1.293 minus 1, so I'll take it as 0.3. Okay, so we got nu as 0.3. You can even try with the third digit or fourth digit, but I am thinking like it's better to take it 0.3 to make our calculation simpler. Okay, and we have seen also, for as you can recognize from the values of nu and g, sorry, E and G. So E and G are little bit closer to what we have seen for the case of our steel. Okay, so these values are commonly for steel mostly. Okay, so we take 0.3. Now we can find the normal strains. Okay, now the thing is, in the question, strain is already given. Okay, that means we know the strains, but we need to find the corresponding stresses. Okay, so the thing is, here we need to find the stresses. Okay, so let's try one by one. So you can see that there are some zeros also in strain matrix. So there is a 0 here, that is gamma xy is 0, and then we have epsilon zz also 0. So we can use that fact, and let's try what comes from them. So first I'll use gamma xy as 0. Okay, so what is given? Given is gamma, because the given is actually epsilon xy is 0, because we know that in tensor representation we put strain as epsilon, not gamma, but we know that gamma xy is what? Twice of epsilon xy. That means gamma xy is also 0. Okay, so gamma xy is 0, so we know the relationship tau xy is g times gamma xy. We just saw that, so that will be also 0. Hence we found that tau xy will be 0. Okay, so this is 1. Tau xy will be 0. Now let's find the other one, the epsilon zz. So epsilon zz is 0, you can see here. Okay, so we'll use this fact also. So epsilon zz is represented by this equation. So if this part is 0, that means this equation will be 0. That means sigma zz will be mu times this. So if we are able to find sigma xx and sigma yy, we can find the sigma zz very easily, and wherever sigma zz is given, we can substitute the value there. Okay, so let's do that. So from this equation comes that sigma zz is nothing but nu times sigma xx plus sigma yy, and we know nu, we'll put nu later on. Okay, we'll put nu as nu. Okay, so this is another relation we got. Okay, now let's see what is there. So this is being used, we can find the tau yz very easily. So tau gamma yz is what? This is gamma yz. Okay, so gamma yz is 0.003. Actually twice of that will be gamma yz. So epsilon yz is 0.003. So gamma yz will be 0.006. Okay, so we have tau yz as g times gamma yz. G is what? For our case, G is 80. So 80 into 0.006 GPa. Okay, remember that the unit is in GPa. So we need to brought it down to MPa, because we usually write our this thing in MPa. So 0.006 into 10 to power 3 MPa. Okay, megapascal, then comes the gigapascal. Okay, so 10 to power 3. So this 10 to power 3 will make this as what? It will make this as 6. So it will become 480 MPa. That is tau yz. Okay. So we got tau yz. Now we'll see for tau. Now we will see for xz. Okay, gamma xz. So epsilon xz is given as minus 0.00002. Okay, so what we need to do, we need to find gamma xz. That will be minus 0.004. That is twice of that. So this becomes tau xz, that will be minus 80 into 0.004 into 10 to the power 3 MPa. Okay, so if you do that, it will come minus 320 tau xz MPa. Okay, so it will become minus 320 MPa. So we got tau xz, gamma xz, tau xz, tau yz, okay, and tau xy is 0. So we got all the shear components. Now the only thing remaining is the normal stress, means normal components of the stress, that is sigma xx, sigma yy, and sigma zz. For that we have the other three equations. So first we will put sigma xx, epsilon xx. So it is 0.001. Epsilon xx is 0.001. So we'll use that fact. So 0.001 is equals to 1 by E sigma xx minus nu times sigma yy. And what is epsilon sigma x zz? We just saw sigma zz is what? Nu times sigma xx plus sigma yy. So we'll just substitute it there. So nu times sigma xx plus sigma yy. So I'll take this E on the left side. So it will become 0.001 into 207, that is equals to sigma xx minus this becomes, I'll open the bracket, nu times sigma yy plus not plus, minus nu square sigma xx minus nu square sigma yy. Okay, I'll club the terms together. So it will be 0.001 into 207 equals to sigma xx 1 minus nu square. Okay, and I'll take minus sign common and nu common and sigma yy common. You have 1 plus nu. Okay, yeah, it will become 1 plus nu. This is one equation. Okay, yeah, so this is one equation. Now we'll use the fact the other one. So other equation being the epsilon yy equation. Okay, so this one equation, and we know epsilon yy is minus 0.003. So we'll use that fact. So for epsilon yy, so it is minus 0.003 is equals to 1 upon e into sigma yy minus nu times sigma xx plus sigma zz will replace by sigma xx plus sigma yy. Okay, now I'll expand this. Okay, so if I expand this, I'll take the e on the other side, minus 0.003 into 207, that is equals to sigma yy minus, I'll open the bracket, nu times sigma xx minus nu square sigma xx and minus nu square sigma yy. Okay, so this will come as minus 0.003 into 207 minus nu sigma xx, if I take common, 1 plus nu, and plus sigma yy, if I take common, 1 minus nu square. This is the second equation. Okay, so we got two equations and two unknowns. Okay, sigma xx and sigma yy. So how to eliminate one of the other? What we can do that, simply we can take one and substitute in the other one. Okay, or even we can multiply. So yeah, but it will be better to take from first equation we can take the value of sigma xx in terms of sigma yy. So that I will write value of sigma xx. Okay, so how you will find sigma xx from equation 1? So it will be sigma xx will be 0.001 into 207 plus it will be nu into sigma yy 1 plus nu and divided by 1 minus nu square, 1 minus nu square. Okay, now this I have to submit an equation, substitute in equation 2. Okay, so minus 0.003 into 207 is equals to minus nu 1 plus nu into this term. Okay, so I'll substitute it here, 0.001 into 207 plus nu sigma yy 1 plus nu divided by 1 minus nu square. Okay, and then plus sigma yy 1 minus nu square. So from this equation you can find the value of sigma yy. Okay, and you know the value of nu, that is 0.3. You can substitute it there and find the value of sigma yy, and then substitute back it here. You will find sigma xx, and then you can substitute these two values in here to find the value of sigma zz. Okay, so because sigma zz is related, so you can find sigma zz using this equation. Okay, but remember that at the end, whatever value you will get for sigma yy and sigma xx, you multiply it with 10 power 3 to get it into MPA. Okay, so I'll write here this kind of homework to you. You can solve it. Okay, multiply sigma xx and sigma yy by factor 10 to the power 3 to get the values in MPa. Okay, to get the values in MPa you need to multiply with 10 to the power 3. Okay, and then you will get the full matrix. Okay, so we have already found the values of sigma tau xy, tau yz, tau zx. Now sigma xx, sigma yy and sigma zz will be obtained from here, and then you have the full tensor for the stress. Okay, so finally you can arrange your tensor sigma stress tensor as sigma xx, sigma xy, sigma xz, or I will write in terms of tau, tau xy, tau xz, tau xz, xy, sorry, tau xy, sigma yy, tau yz, tau xz, tau yz, and sigma zz. This will be the answer finally. Okay, so that's how you will solve the first problem, where you are given the strain tensor, you are given the Young's modulus and shear modulus value, and how to find the stress tensor. So first, using the Young's modulus and shear modulus, you find the value of the Poisson's ratio, and from that value you can substitute it in the Hooke's law, that is three-dimensional Hooke's law, and you can find the corresponding values of sigma xx, sigma y and sigma zz. Okay, and the value of tau x y, tau yz and tau xz are very straightforward. Okay, now that's how we'll do the first question. So I believe you guys have understood. Is there any doubt? Let me know in this, because this is the very basic problem in consideration. One of the thing is given and another is need to be found. Okay, so I've taken this week for this only, because this is the basic thing, how to relate the strain with the stress. Okay, and these are called constitutive relations basically. So Hooke's law is also a constitutive relation. Okay, so now we'll go to the other problem, the second problem. Okay, so there is one more problem we'll solve today. Let's see what is that, and this is more interesting. So in this case, in this question problem, a square plate of side 10 cm and thickness 1 cm is subjected to the following state of plane stress. So this is the plane stress is given, it is a state of plane stress, and this is the square plate. So its sides are of 10 cm and its thickness means this dimension is 1 cm. Okay, okay, and the state of stress is represented by this tensor, this plane stress tensor. Okay, now assume that the plate is made of steel. So we are assuming that plate is made of steel which obeys the isotropic Hooke's law, and with Young's modulus as this and the Poisson's ratio as this. For this state of stress, compute the following quantity. So we need to find these quantities using this state of stress. Okay, so what all we need to find? So we need to find the strain tensor components, epsilon xx, epsilon yy, epsilon xy, epsilon zz, and then we need to find the change in volume and change in thickness of the plate. Okay, so let's attempt this. So are you guys able to see my screen? Okay. Is it visible now? Yeah, okay, thank you. Okay, so we'll use this stress tensor to solve this problem, and this is the other way problem. So first problem was that a strain was given and we was asked to find the stress. In this, stress is given, and let's see how we find the strain, and let's see then how we find the different changes. Okay, so now we'll solve this one. So the stress tensor sigma is given as -20, 30, 0, 30, 60, 0. Okay, so this is our stress tensor. Okay, it's all in MPa. The units are very important because we need to find some changes, like change in angle, change in volume and change in length or thickness basically. So the units are important here. Okay, so now let's go to the expression where we need to find how we find the strain. So we find the strain. Again I need to write the similar expression to find the strain from here. So we have epsilon xx as 1 upon E sigma xx minus nu times sigma yy plus sigma zz. Okay, so in this problem also E is given, it is 200 GPa. E is given 200 GPa and nu is given 0.3. Okay, so what I will do, I'll substitute the quantities which are given. So 1 upon E sigma xx is given -20 minus nu is 0.3, sigma yy 60 and sigma zz is 0. Okay, so it will be and I'll also substitute the value of E, but I will substitute in MPa. So 1 upon 200 into 10 to the power 3, that will be the MPa, and -20, and this becomes 18, -18, so it becomes -38. Okay, so it becomes minus 19 if you divide by 2, and that 2 10 to the power -5. Okay, so that we get the strain epsilon xx. Okay, so how else we can write it is minus point naught naught, or no, 1 naught only, minus 0.019 into 10 to the power -3. Okay, and then we can write mm per mm. Okay, yeah, so this we got epsilon xx. I think this is part A. Part B will find epsilon yy. Again we know 1 upon E sigma yy minus nu times sigma xx plus sigma zz. Okay, so this is 1 upon 200 into 10 to the power 3 sigma yy 60 minus 0.3 minus 20, and sigma zz is 0. Okay, so it becomes 6, so it becomes 66. I'll divide also, it will become 0.033 into 10 to the power -3. Or what I will do, I'll do in 10 to the power -5. So better is I'll write like this, minus 190 into 10 to the power -6 mm per mm. That will be better. Okay, so we can say micro strain. Okay, yeah, that will be better. So here also it will come out to be 330 into 10 to the minus 6 mm per mm. Okay, correct. And now the C part will be epsilon zz. First we will solve all epsilons. Okay, so 1 upon E, and this will be sigma zz minus sigma, okay, to nu times sigma xx plus sigma yy. Okay, so now we know that sigma zz is 0. So here you will see that how a plane state of stress can also can generate a triaxial strain. Means strain will be there, but stress won't be there. So you can see for this state of stress there is no sigma zz component. Okay, that is absent there, but still the strain component in epsilon zz is going to be non-zero. Okay. Okay, so that's what the professor was telling. Even in case of the uniaxial tension test, which you apply sigma yy in the uniaxial direction, but still you have epsilon xx and epsilon zz strains. Okay, until unless you have constrained it. Okay, okay, so that's very important here. Yeah. 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 That's what. That's what. Even if the state of stress is plane stress, the state of strain won't be plane. Okay. Even your stresses are lying in one plane, the strain won't lie in one plane until and unless it is been confined. Okay. There is some confinement given. Okay. So in general this happens. Okay. So that's what we say, that the state of plane strain or plane stress may not lead to a state of plane stress. Okay, so if you have in this example, that's why I have shown. So in this example we have a state of plane stress. This is a plane stress, but you can see that we will have a non-zero value of plane epsilon zz, that is the plane which is out of the plane of the plate. Okay, so this is the plane which is out of this of this plate. Okay, so but that will have a strain. Okay, yeah, in the thickness direction, z will be in the thickness direction, so there will be a strain in the thickness direction. That is the point. Okay, so that will be there. Yeah, so because of the Poisson's effect. Okay, because this we are using, if this was not there then it would have been zero very easily, but that's not the way. There is the Poisson's effect, so because of that effect it comes in the other direction. Okay, so if you elongate a body in a uniaxial direction, it contracts. For a Poisson's ratio, positive Poisson's ratio, it contracts. For the negative Poisson's ratio, it will bulge. Okay. Okay, so let's substitute. So 1 upon E. So this is 0 minus 0.3. This is minus 20 plus 60. So this will come out to be 40. So I think 120 into 10 to the minus 6 mm per m. I hope I am correct here. It will come out to be yeah, correct. Okay, okay, and then D component will be, we'll find the epsilon y xy, epsilon xy. So we know that how to find epsilon xy. We know that gamma xy is nothing but tau xy by g. What is tau xy? It is 30 MPa. And what is g? Now we need to find this g. and how G is related, G is E upon 2 1 plus nu. So it will be 200 divided by, it will be 2.6 around. Okay, so what this quantity will come out, I'll just calculate. So it is 200 divided by 2.6, so it will be somewhat 76.92 MPa. Okay, so we need to use that in there. Okay, so we'll use this there, so we'll get gamma xy is tau xi, so tau is 30, so 30 divided by, sorry, this won't be in MPa, this will be GPa, okay, because E is in GPa, so it will be 76.92 into 10 to power 3. Now this will be in MPa. Basically it won't be in MPa, but it will be in mm per mm. So I'll find this value. So we have 30 divided by 76.92. Yeah, so it will be 0.39 into 10 to the minus 3 mm per mm. So it can also be written as 390 into 10 to the minus 6 mm per mm. Okay, so the epsilon xy will be half of this. Okay, so it will give us 195 into 10 to the minus 6 mm per mm. Okay, yeah, so that's how we will find the epsilon xy component. Okay, now, so we found these all components, so now I can create the other. Okay, other components will be 0, because you know that tau xz is 0, tau yz is 0, so this would lead into it's interesting to note that G being almost 1/3 of E, you can appreciate that the material will have more shear strain than normal strain for a constant value of normal stress, shear stress. Yeah, 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 it will be, yeah, 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 it will be higher, but it also depends like on which plane you are acting or in which plane you are seeing that. Okay, so because if you will change the planes, this matrix will change if you change the planes. Okay, so there some planes you will find that there is no shear strain at all. Those will be principal planes, and some plane you will have higher values or even maximum values. So as we have gone through the Mohr circle for stresses, there is a similar Mohr circle for strains also. Okay, so if you see for the case of pure shear, the Mohr circle will be about center basically for strain also. So when it will be about center, so the radius of the Mohr circle will remain same. So that means whatever is the value of shear strain is the same value of maximum normal strain also. So that is an example, one of the example. Yeah. So that we can say, but yeah, obviously the strength or the ability of the material to resist shear strain will be lesser than that of the uh, yeah, yeah, that's so. And that's how we have seen that the cup and cone fracture which we have seen in the failure in the mild steel bars, so they actually happen on the plane where you have shear more, okay, 45 degrees. Okay, when we apply uniaxial tension, so a plane which is in the whose direction is similar to the direction of the loading, it doesn't fail in the ductile materials, but it fails at 45 degree from that plane. That means it fails on the plane where the shears are more prevalent or more are higher, and we will see this also later coming to the in the failure theories. So next, when the failure theories come, you will see that how the for ductile materials how shear strain is more relevant criteria than the others. But for brittle material, that is not the case, as you have seen in the case of chalk. So when the chalk is loaded, it is actually, so it will fail on the on same plane where the load whose normal is parallel to the loading. So yeah, so that is the property of ductile materials to fail in by shear. Okay, so all the calculation where we are doing for those only. Yeah, so I was saying that gamma yz xz and gamma yz both will be 0. Okay, so we can formulate our whole epsilon tensor, strain tensor. Okay, epsilon xx is minus 190 minus 190 tau xz will be 0, here it will be 0, and then this will be 0, and then epsilon xy is 195, and then zz is minus 120, xz and yz both are 0, so this will be 0, and yy is 330, so this is 330, and this will be 195 into 10 to the minus 6. Okay. Okay. So that's how we will get the strain tensor. So you can see, although our loading was a principal stress, okay, but the strain is not plane stress, the strain is not plane, okay, it is having a ZZ component, out of plane component. Now only the way to avoid this is to restrain it or to constrain the other direction. So if you put a heavy block of mass in the other direction, it won't generate. But what it will generate the stress in that. Okay, if you will constrain this strain here, so it will generate a stress. Okay, so that is there. Okay, now now we need to find two things. One is the I think change in volume. So change in volume of the plate, and you need to find the change in thickness of the plate. Change in volume in mm cube. Okay, so as you have gone through the lecture, professor also told something about bulk modulus. So how we find the change in volume. So there is something called volumetric strain. Volumetric strain, which is represent delta V upon V. Okay, change in volume upon total volume, and it is nothing but epsilon xx plus epsilon yy plus epsilon zz. This is the volumetric strain. So delta V upon V will be we already know the value of this. So if we sum it up and see, so it will be 330 minus 310. 330 minus 310 into 10 to the minus 6 mm per mm. Okay, 330 minus 310. So this will be delta V will be 20 into 10 to the minus 6 mm per mm. Okay, now we need to find the change in volume. So delta V will be 20 into 10 to the minus 6 into V, that is the original volume. I'll write right now V, that will be in mm cube. I'll write V in mm cube. Okay, now let's see what is V. So V is, we know that the length and width of the square is 10 and the thickness is 1. So 10 is in centimeters, so it will be 100 mm into 100 mm into thickness is 1 centimeter, it will be 10 mm. Okay, so it is nothing but 10 to the power 5 mm cube. Okay, volume, original volume. So delta V will be what? It will be 220 into 10 power minus 6 into 10 power 5 mm cube. Okay, so it becomes 2 mm cube. Correct? 2 mm cube will be the change in volume. Okay. Okay, so we found the change in volume. What is the change in volume of the plate? Then the last part of this question is find the change in thickness of the plate. Now we need to find the change in thickness. Now you know that from the figure what is the thickness direction, because we need to know which direction is the thickness direction. So it is the out of this plane direction. Okay, that is the thickness direction. Means this, if I draw some plate like this, so this out of plane, this is the thickness, and which is given as 1 mm. Thickness given as 1 mm, and it is in the z direction, out of the plane. That means we need to deal with what? We need to deal with the zz direction, or z direction basically. So we need to find, use epsilon zz to find change in thickness. Okay, so let's see. We know what is strain. It is change in length over the total length. So let the original thickness before deformation is given by, so suppose it is given by h, okay, and we know what is h is 1 centimeter. So what will be the epsilon zz? Epsilon zz will be delta h upon h, okay. Now we need to find what delta h. So delta h will be epsilon zz into h, okay. What is epsilon zz? Epsilon zz is minus 120. So minus 120 into 10 to the minus 6 mm per mm, and into h in mm is 10 mm. 1 centimeter is 10 mm. So this mm. Therefore minus, it will be 120 into 10 to the minus 5 mm. So that this will be the change in thickness of the plate. Minus 120 into 10 to the minus 5, or 0.0012. You can also say minus a point. So basically you are seeing that it will decrease in thickness. Thickness will decrease. Okay. So you are seeing that the volume will increase by 2 mm cube. Okay. But the thickness will reduce. Okay. So that's how we can use the various strain components to come up with this change in volume and change in thickness. Even if we want, we can find the change in length in x and y direction, because we have the strains in x and y directions. Okay. So in similar fashion we can do that. Okay. So I'll do one example here. Change length of, or change in length of plate in x direction. So it will be what? Suppose that is delta L. So delta Lx upon Lx, that is the length in x. So this will be what? Epsilon xx. Okay. Now what is delta Lx? It is epsilon xx. What is epsilon xx? Minus 190. Minus 190 into 10 to the minus 6, and that into Lx. Lx is the original length. We know that Lx is 10 centimeter. Okay, so it will be 100 mm. Okay, 100 mm. So delta Lx will become minus 190 into 10 to the minus 4. This will be mm here, mm. So basically 0.019 minus mm, that will be delta Lx. Okay. So delta Lx means change in length in x direction will become this. And don't think that delta Lx will be same as delta Ly, because there is a different strain in y direction, so it will be a different magnitude. So you can see that there will be a reduction in the length in x direction. Okay. So but don't think that the same change will happen in the other direction. It could be different because of the somebody may consider that there is a same length, so the change will also be same, but that is not the case. The change could be different because it all depends on the magnitude of the strain. Okay, how the strain is calculated. Okay. Yeah. So anyone is having any doubt in this? Yeah. Yeah, any doubt in these two problems? Okay, okay. Thank you, Arjun. Yeah. So what we'll do, we'll solve one more problem on thermal strain. Okay. So we'll try to solve one problem on thermal strain. Okay. So although I had come with these two problems only, but we'll solve one problem on thermal strain. So suppose okay, so suppose we have this inner one is a plate. Okay, this one is a plate. Okay, and suppose this dimension is 20 centimeter and this one is 10 centimeter. Okay, and this length is suppose, and this plate is kept in a cavity. Okay, so this is basically a cavity. That means this area is free, open, nothing is there. Okay, there is nothing here in this area. It's a open free area, no material is there, and these are some rigid boundaries. Okay, these are some rigid boundaries. So what I will do, I'll put something like this, so to show you that these are rigid. Okay, they won't move, they are rigid. Okay, so and this plate is kept such that it is in the center of this whole thing. Okay, it may not look like right now it is in center, but consider that it is kept in center. Okay, and what I was mentioning, that this length is 22 centimeter. Okay, and here it is 12 centimeter, or maybe 11 centimeter. Okay, okay, so the problem is that we have a plate, it is made of steel, so we have steel plate. Okay, and the dimensions are as given here. For the inner plate, so basically the inner one is the plate and the outer one is a rigid boundary which can't be displaced, and the area between these two, this area is a free area. Okay, so that is there, and let's take that this plate is made of some material whose, so we'll take for the steel itself. So steel, what all we know, that we know E is 200 10 to power 6 plus 200 GPa will write 200 GPa, nu is 0.3 and we'll take the coefficient of thermal expansion or linear expansion alpha as 12 into 10 to the power minus 6 per centigrade, okay, per Celsius. This is the value, I think, for alpha for steel. Okay. Now, what happens that the plate is heated, the inner plate is heated to a temperature of, means it has been heated, so there is a change in temperature. So, change in temperature steel plate is 200 degrees Celsius, suppose. Okay, so suppose room temperature was 25, so I made it till 225 degrees Celsius. So there was a change in the temperature of the plate. Now we need to find what will be the stresses, whether there will be the stresses, or if there will be, what will be the magnitude of those stresses. Okay, that is our goal here to find. Okay, so we have to use some of the properties which professor has told already in the class, in the lectures. So you know that if there is some body, so let's see in this sense. So suppose a body is there. Suppose this is the object or body made of any material. Suppose this is a body made of any material which has some thermal, which has some coefficient of linear expansion. Okay, it is non-zero, that coefficient of linear expansion. Okay, and if you put a heat source to this body, so this is the heat source. Okay, you put a heat source to this body, so its temperature will increase. Okay, so when the temperature will increase, what will happen? This body will also increase in length. Okay, because of the alpha value, it will change its length. But you know that what happens with alpha? Alpha only changes normal strain. Okay, alpha does not induce shear strain. Okay, basically it does not induce shear strain, it only induces normal strain. Okay, so if you look in another sense, the coefficient of thermal expansion only tries to change the volume. Okay, because of the, you know how the volume is related. See, the best example we have just seen how the volume is related. Everything is here. The volume is related based on the normal strain, not the shear strain. Volume change doesn't depend on shear strain. So the alpha doesn't affect that. The alpha only tries, or the heat basically try to expand the body. So by expanding, we mean by there is a change in volume, but it doesn't try to change the angle. It doesn't try to distort the body. Okay, but the shear strain is that shear strain tries to distort the body. It changes the angle. Okay, so that knowledge we should have, that alpha, it only changes the normal strain and does not induce any shear strain. Okay, so what I was trying to say here, that the body, when this body is heated up using a heat source, this will cause a change in temperature of the body, and I am assuming that the heat is applied in a uniform manner. Okay, I am assuming that it is in a uniform manner, although we can have different approaches in which we will have uneven type of heating. So basically this end will be heated more and this end won't be heated or very less heated. So that is actually a current ongoing research topics. Many people have taken that as a research interest. So how it happens, how it changes the various stresses inside the body, that is the residual stresses also, how it alters the residual stresses. But most of these things are done for very high temperature. Right now I am taking till 200 degrees Celsius, but that has been done for very high changes. And when I'm saying 200 degrees Celsius, I am assuming that there are no change in the elastic constants. Okay, professor told in class it will remain till 100. I am just like, for the case of this problem, for the sake of this problem, I am doing. It is not like that. It is correct that the properties will remain same. The elastic properties will remain same till 200 degrees Celsius. They will change after 100 degrees Celsius, but little bit, like 3 or 5%. Within 5%, they will be up to 200. Most of the changes comes after 430, 500 degrees Celsius. That are very high changes, like some 30-40%. Okay, so I'm ignoring that 2, 3, 5% or even 10% that will happen with 200 degrees Celsius change. Okay. So now point was, when I apply a uniform heat source on this body and which causes a change in temperature, what happens? The body tries to change in length. Okay, that is the strain comes in picture, and that it tries to expand. Okay, so if there will be a positive change in temperature, it will expand, and there will be a negative change in temperature, it will contract. Okay, now there is no restriction for the body to change its length. No, so it will become something like this. The body can become something like this. Okay, because there is no restriction on the body, so it will change as per as it suits. Okay, but what happens if to the same body, what happens for the same body if I do what? If I put a restraint here, I say it can't move this direction. Okay, and again I put a heat source. There is a heat source here. This is the heat source. Okay, and I put a restraint. So what will happen? Now the body can't extend in this direction, or can't change the length in this direction. That means it can change, but it can change in this direction. So what will happen? It will change the it will cause a strain in this way. Okay. Okay, so in the first case, you will see that the strains will happen, there will be a change in length in the body, but there won't be any stress induced. Okay, in the first case, there won't be any stress induced, only there will be a change in the length, that there will be strains but no stress. In the another case also, we have restrained the body at one end, but the other end is still free. Okay, here both ends are free. Here one end is restrained, one end is free. So still the body has a way to increase or change its length by inducing strains. So it will change the length in this direction, and again the body will have strains, normal strains, but it won't have the stress because it can extend. Now what I do in the final case, I restrain the body from both the sides. Now I restrain the body for the sides, and again I put a heat source here. Okay, like this, heat source. So now what will happen? Because of this heat source, the body will try to expand. It will have developed strain, so it will try to expand in this, but there is a boundary which won't let it expand. Therefore, there will be some stresses will be induced. So only when the body, which is subjected to some thermal loading, is restricted from undergoing deformation, okay, is restricted from undergoing deformation, then only it induces some stresses. Until it is not restricted, it is free to move, it doesn't induce any thermal stress. Okay, it doesn't induce any thermal stress. So very common mistake that we think that the body is there, and if there is a change in temperature, so until the temperature is until the body is restrained or not, we don't care about that, and we just simply find the stress. We say strain is alpha delta T and stress is E times strain. We find the stress. but that's not the way. Stress will only occur when the body which is subjected to thermal strain is restricted from undergoing those strains. Okay, that is the third case, this case. Okay, so that we have to keep in mind very, very carefully. Okay, now coming to our problem. So we have this this thing. So this thing, now the plate in between, I said that it will be heated so that there is a change in temperature up to 200 degrees Celsius. So what I was explaining till now was to make the point that when this plate will be heated, it will keep on increasing in its length, something like this. Okay, it will keep on increasing in length. So what will happen? Till the time the body does not touches, or the plate does not touches these edges, do you think it will have any shear, any stress, specifically stress induced due to thermal? Do you think? Till this edge doesn't touch this edge, or till this edge does not touch this edge, will there be any thermal stresses induced? Yeah, correct. No, because there is no contact. Okay, but do you think there will be thermal strains? Yes, because we are applying a thermal loading, so it will cause a thermal strain, but it won't cause a thermal stress. So when it will cause a thermal stress? Only when it is restrained. So till the time this body does not, this edge does not touch this, and similarly this edge does not touch this, and for other edges it won't cause any stress. Okay, so that's how we'll have to proceed in this problem. Now let's solve it. So that means we need to cause this much of, no, so as we came to know that till this edge does not touch this, this edge does not touch this, this edge does not touch this, and this edge does not touch this, there will be no stresses induced. Now I want to find, my question is, I want to find what will be the stresses. That is my question here. If this is the thermal loading and this is the thermal loading, this is the parameters, what will be the stress and whether it will be or not. First of all, I should know whether it will be or not. So that we can know when the strain induced due to thermal loading will exceed the strain which exceeds this length, basically this much length. If it will cover, means while expanding, if the body is able to cover this much of length, then only it will be able to induce the stresses. So first what we will do, we will find what will be the thermal strain. Okay, so as you know, the professor has told you in the class also, in the lecture also, that when we add up the thermal strain, we add up thermal strain in all the normal strains. Okay, that is epsilon xx, epsilon yy, and epsilon zz. That means every component will be having the thermal strain and the magnitude will be same, because there is the assumption that it is uniformly heated up and it is expanding also uniformly. That here we are not saying that this alpha thermal alpha coefficient, that is the coefficient of linear expansion or coefficient of thermal expansion, is different for different direction, because we have assumed that the body is isotropic. Okay, if for a problem this alpha is different for different directions, it could be we can make a body, we can make a material which will behave in a manner which could have a different linear coefficients of linear expansion in 3 directions. Then we have to take up that accordingly in the expressions for the strains also. Okay, but for now, as we live in very simplistic linear elastic and isotropic material domain, so we can just say that our strains will be same because of the thermal loading. So epsilon xx will be what? Alpha delta t. Similarly, epsilon yy will be what? Alpha delta t, and epsilon zz will be what? Alpha delta t. Okay, but if this case would have been the other one, that the other one means that the value of the alpha is different for different direction, then this would have been different. Okay, now let's compute this. So we have alpha as 12 into 10 to the minus 6, and we have a 200 degree Celsius change in temperature, which will give us 24 into 10 to the minus 4. that will be mm per mm, and this will be same for each. So I will write as epsilon yy is equals to epsilon zz. Okay. So now coming to the problem, as you see there is nothing, no restriction in z. Okay. This is I will specify, this is y, this is x. So z you know out of plane, this is z. Okay. So you can see there is no restriction in z. Okay, I have not provided any restriction in z. Only restrictions are in x and y. So in z it can go as much as it wants. There is no restriction at all. Okay, but we need to see what happens when it is restricted in x and y, because there we have put some restrictions on the boundary, and then we have to check whether it is feasible for it to expand or not. Okay. Okay. Now, as I told, we found what is the strain incurred or induced by thermal loading. We have already found what strain it can incur. Now we need to find what will be the strain in this longitudinal direction, this x direction, and what will be the strain in y direction. So how we have to do? So we know what is the original length. This is the original length of the plate. What will be the final length? We know what will be the final length. So we can find the strain out of that. Similarly, we know the original length. This one is the original length of the plate in y, and we know what is the final length in y. So we can find the strain in y also. Okay. So, and we are finding this strain assuming that it has increased. So you can see the maximum available strain in x direction without inducing thermal stresses. Okay. So what it will be? So we will say epsilon xx, it will be, I think 2 mm is the difference. So 2 divided by 20, yeah, I think 20 only. Yeah, 2 divided by 20, that is 0.1 mm per mm. Okay. And similarly we can find in yy, it will be 1 divided by 10, and that will be also 0.1 mm per mm. How I wrote 2 and 1, you know that I found the change in it. Okay. That means, see, so what is your thermal, this thing is 24 into 10 to minus 3. What is your actual available, this thing is this. That means it can easily expand in that much. So there will be no strains at all, because it can very easily expand in that much area. Okay, in this much area. Okay, but what happens if I change this alpha? Okay, right now I put this as 10 to minus 6. Suppose I remove the 12 to minus 6 at all. I make it 10. Alpha is 10. Okay, when alpha becomes 10 or alpha becomes 12, then you see how it changes the strain. Strain will become very high. Or even if you can see 10 to the minus 4. So even if I make this alpha as some 10 to the minus 12 into 10 to the minus 2, that is 0.12. If I make alpha as 0.12, how it will become? It will change. It will become 24 or something like that. And then your epsilon xx, that is the thermal strain induced, will be more than the epsilon xx, which is available there, and epsilon yy available there. Okay, I will write here in x and y direction. Okay, then it will be more. So how to find then stress? So I will say, I will write this as available. Okay, available, and that is thermal. Here it is thermal, th, thermal. Okay, now So what will be the effective strain? So you will find the effective strain. Effective strain. This effective strain will come, so I am writing the case when epsilon thermal is greater than epsilon available. Okay, that is also called as observable strain also, or mechanical strain sometimes. So we'll find what? We'll find epsilon effective. Effective strain will be epsilon thermal minus epsilon available. Now you understand why I'm reducing it, because that much strain it won't cause any thermal stresses. This we get the effective strain, and from there epsilon effective, what I can find? I can find this I can equate to 1 upon this sigma xx plus minus minus mu times sigma yy plus sigma zz. So this will be effective of xx. Then we'll have epsilon effective the other direction also, yy, 1 upon e sigma yy minus nu times sigma xx plus sigma zz. As you know, for this case sigma zz won't be there, because I told there is no restriction in the z direction, so sigma zz will never induce, so it will be always 0 sigma zz. So we can just remove the sigma zz. So we have two equations. We will be knowing the left hand side part, this and this. We have two equations and two unknowns, and we know E and mu. We can find sigma xx and sigma yy. Okay. So that's how we can find the value. I hope this you understood, this one. Yeah. 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 Yes. Yeah. And the similar thing. Yeah. Yeah. You had to ask something. Yeah. Yes. 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 Yeah. Which is, in our case it is lower. Yeah. In our case it is lower. So that's why I was not able to follow it more further, because I had chosen some random dimensions. If I choose it appropriately, the dimensions as well as the material for steel or some other copper or brass, then we can solve a problem with that. I will do this problem next time. Actually, I was, yeah. Yes. It doesn't touches. It expands, but it doesn't touches. It doesn't touch. Correct. 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 Yeah. So we'll solve with a proper problem next time. The same problem I'll come up with, and with a proper this thing, and we'll solve it. So we'll see how the thermal strain causes the stresses. Okay. So yeah. Yes. 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 Yeah. 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 Hmm. Hmm. You mean to say when he's solving a pipe problem with a pressure thing? No, the question you are asking is related to that question in the lecture where there was a pipe and in that pressure flow. Yeah. Yeah. Hmm. Yeah. Yeah. Hmm. Yeah. Hmm. Hmm. Okay, okay. I'll try to explain the simpler problem. I'll don't go. I won't go in that problem of uh, the problem which professor solved, that circular cross section. I'll do a very simple problem. Okay. So let's take an example that I have made a composite bar. Okay. This is of brass and this is of steel, and this is the interface. Okay, this is the interface, and the given is that alpha for brass is far greater than alpha for steel. You have seen alpha for steel is very small, but alpha for brass is very far. I am saying it is very far greater than. Okay, now it is subjected to some heat. Okay, some temperature change. So what you observe? But you observe that, and for the sake of simplicity, I will restrict this edge. I'll say this is restricted edge. Okay, this is restricted. So it is not moving that direction. It has to move in one only. Okay. Now, as you know that alpha for brass is greater than alpha for steel. So tell me in which one you think for the same change in temperature, which will have more strain? Brass will have more strain. That means the brass will have more change in length compared to the steel. Okay. Okay. So what I'll do, I'll draw the deformed shape of brass. So it will be something like this. And the steel will also change, but it won't change that much. So it will change this much only, very less. Okay. Now, if we assume that the brass and steel are going to be deformed independently, what I have drawn is perfectly fine. If there is no interface at all, means the two materials are not glued together or they are not together, acting together. Okay. So, if I say that, then the way I have made it is perfectly fine. Okay. And that should be the behavior if they are acting as two different parts of the same body. Means the system is containing brass and steel both, but if they are not have the same continuity or if they are not have the same compatibility, then they can deform in the way I have shown. But and if there is no interface, they are not connected somewhere, then it will be happening this way only. But what happens if there is an interface? So, what happens if there is an interface between the brass and the steel body? This interface is then comes into the play. Now, what it does that, it's like the interface is like a conversation between two people. Okay. What will happen? Okay, brass will come and sit here at the interface, steel and come will sit here at the interface. Now, brass will say, okay, I have to extend by 10 mm. Steel will say, no, that's not even possible. I can go for 2 mm. That is my maximum. So, there is that conversation is happening at the interface. And what is that conversation? That how much we should expand, because we are together. We are together with this interface. So, we have to decide our fate by sitting together. We can't do it independently. We could have done it independently if there was no interface. We didn't need to sit here and talk. We can do whatever we want. But now we have an interface, common interface. We have to satisfy that compatibility because we are connected together. So, we should either expand or contract together. That means the strain in both the things should be same, brass and steel. How much, that will be governed, but it should be same. Okay. Now, yeah, because why it is to be same, I will just explain. Because the brass is trying to expand more than the steel. Okay. So, till the time the steel, as I told, I will write. Okay, I am giving a very rough estimate. Suppose the capacity of brass to expand using the same alpha brass and delta T is 10 mm, and the capacity, this is for brass, and for capacity of steel to extend is 2 mm. Okay. So, suppose I start heating this system, what will happen? Till 1 mm, will brass and steel will have any problem? Till 1 mm. If it has expanded 1 mm. They won't have a problem. Till 2 mm, they won't have a problem. As soon as this extension keeps on increasing after 2 mm, now that extra extension, 2 mm it was allowed in steel. Now, if suppose brass keeps on going till 3 mm, it says no, we have to go together. Okay, let's go till 3 mm. Now, that 3 mm minus the 2 mm which is already allowed in steel, that extra 1 mm will start causing a tension in this one, in the steel. It will start causing a tension in the steel one, and otherwise it will cause a compression in brass, because the steel will try to pull the brass back. It will say no, come from 3 mm to 2 mm, and the brass will say no, we have to go to 3 mm. So, basically the steel will exert a compression on the brass and the brass will exert a tension on the steel. Now, they have to come at par, somewhere they had to come at par, or somewhere they have to settle down. That somewhere where they have to settle down is defined by the strain. Because how you will ask them to settle? So how you will define that where they have to be settled, where they have to settle, that will be defined by the strain. What is the strain they can come up, how much strain extra they can come up. I am not saying that it will happen at the thermal strain itself. No, I am not saying that alpha delta T will only play the role. No. There will be certain extension. That's what you have to compare the full strain, which professor wrote in the class also. So he said what epsilon xx will be what 1 upon E sigma xx minus nu sigma yy plus sigma zz plus alpha delta T. Now you have to do this for both of the material, brass as well as strain. So basically you are satisfying the compatibility of this, not only the temperature. In this case I am saying, okay. So basically you can satisfy the compatibility by strain, yeah, and we usually satisfy the compatibility by strain only. Okay. So now what we can do, yeah. No, see, that's what I am saying. The sigma xx, yeah, as you know, as what I told in the last time, that until the sigma xx won't increase above some limit, okay, or the thermal strain won't increase above the required this thing, it won't cause any thermal stress. You know that this is a case of free expansion. As I told in the 3 examples above, this was free, there was no stress will generate, only in this case stress will generate. But in this case there is a reason for the stress to generate, and that reason is the interface. If they were 2 different materials without any interface, they would have extended on their own and there would have not been any stress generated. But because they have a common interface, they have to follow the compatibility of the strain. Basically, I won't say this is the compatibility of the thermal strain. No, it will be the compatibility of the total strain. This is called the total strain, not only the thermal component. Because suppose the extension allowed using thermal strain is suppose of 2 mm. No, corresponding to this strain, there will be a certain extension allowed. Suppose that is 2 mm. So steel doesn't have any issue to extend till 2 mm. And similarly, brass independently doesn't have any issue to extend till 10 mm. But when brass starts pulling steel after 2 mm, then this sigma xx will set up. Till then there will be no sigma xx. Till this 2 mm, there will be no sigma xx. This whole thing will be 0. But as soon as you go above sigma xx, this 2 mm, you go extension of the steel part above 2 mm, this sigma xx will set up. And what this sigma xx will do, will try to pull the brass part back, and hence in the brass also there will be a sigma develop. Yeah. Yes. Yeah, exactly. Then the thermal strain will be same. Yes, because they have to act in unison. They can't act separately because they share a common boundary, common interface. Okay. If they would have acted in their own way, then it would be a different case. Okay. Yeah. The total, actually, it is still not a correct way to say the thermal strain will be same. Best way is to say total strain will be same. You can't say thermal, because if you go beyond, suppose in the final the total extension of both bars is suppose 3 mm. Now the extension 3 mm won't ensure that there is no thermal stress. It will ensure there is a thermal stress. So you are going beyond the value of 3 mm. So basically you will be comparing or saying that the strain, the total extension should be same. be it without thermal strain or be it with thermal strain. Means what I am trying to say, be this equation be there or not, it will depend on how much you have heated the system. Okay. If you have heated so that this will remain till 1 mm, then it will be in different way, but you have to see at what is the value here. Okay. Suppose you have heated in a sense that, suppose you have heated the brass, this whole system, in a sense that this extension is only 1 mm. So obviously we know the extension in steel will be very, very less than 1 mm. That means there is no stress generated still. It won't generate any stress. But yeah, the both system will move together, but they won't generate any stress. Suppose in the brass the extension is 2 mm. Still there won't be any stress generated, because that is allowed to expand that much. Even because this is 2 mm brass, so obviously steel will be far less than 2 mm. That is my point. Okay, and the best example of this compatibility of strain is our reinforced concrete beam. That is the best example, no? You can visualize in another sense that what is happening in our concrete beams. There is a compatibility strain between the surface of the rebars and the concrete attached to that surface. That is an assumption. We say that it's an assumption there, but we that's how we would do our everything, full working stress method or limited state method or anything like that. We say that there is a compatibility between them. Yes. Where? Yes. Yes. This is one example I have given where we consider it like, although it is achieved or not, is it possible to achieve that? In word loading cases it is possible to achieve that. It is debatable, but there is an assumption in the theory where we design such things, such beams, we take it in that manner. Yeah. Yeah, because we are, why we are doing that, because it should have a single strain. Bar should have a single strain. No, it can't happen that this portion of the brass portion should bulge out and this goes below. No, it can't happen. Similarly, the cases where we have a circular bar is there. So you have suppose one material is here. Okay, whatever you can take, copper you can take, suppose this is copper, and inside copper this is suppose your steel. The inner one is the steel and outer one, so even better than this. So suppose this is a casing, of steel, and the casing of steel is the casing of steel is this is void here. So the casing, this is steel, inside is steel, and this could be copper. Or best example is zinc, where galvanization, we do galvanization. No, so what we do, we dip the casing, suppose some rod or some pipe member is there, we want to protect it with the corrosion. So what we do, we dip it in the molten zinc, that is galvanization. So what it does, it creates a layer of zinc metal over the surface of the other one. Like suppose if it is the steel pipe, then it will be a steel. If it is a cast iron CI pipes, then it will be a CI. Okay. So suppose it has some thickness. So obviously there will be a difference in the thermal expansion of both the materials. But still, what we say that the strain in both will be same. There will be compatibility of the strain between the interface of both. They won't be like the copper or zinc will extend more and steel will extend less. No, they will have same strain. Yeah. 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 Yes. Yes. Sure. You have to satisfy the force equilibrium. Forces will be same. Yeah. Yeah. So the stresses which are generated are because of the thermal loading. Yes. Yes. Yeah. Yeah. Sure. It comes back. Yes. It depends like how the material properties are there. Okay. How the material manufacturing process has been adopted. What how is the, because this coefficient of thermal expansion, linear expansion is for both ways. It is like for change, positive change as well as negative change. But obviously there are certain limits. Okay. So if you see the uh, if you see the temperature versus stress diagram for steel manufacturing. So if you specifically go in lower temperature, you will observe that the steel becomes brittle after maybe around some 100 degrees Celsius, minus 100 degrees Celsius or minus 150 degrees Celsius. I'm not sure with the figure what is the value of that temperature, but it essentially becomes brittle after, and that has been case of some of the spectacular failures which professor has shown in his first or second class. You might have remember the class of where he showed the ships in the second, during the and after second world war. Yeah. So they were breaking, actually the ships were breaking in two halves and they were made of steel. So how come steel can fail like a brittle material? The ship didn't show any ductile behavior that it is going to fail or some very huge extensions are happening or very large strains are coming. Although that is the property of steel, but at normal operating temperature, not at very low temperature. So it failed there, and they had some spectacular failures like the bridge the ship got broken at the center. From the middle itself, it broken into two halves, like a brittle material. So it depends like how the manufacturing process for the steel or the material has been adopted. But yes, it comes back. If you, even in this problem, if you have a negative heat source, or like if you are taking heat out of the system, then it will reduce in the length instead of increasing. Yeah, exactly. So yes, so the brass will reduce more than the steel, then the thing will be different. Right now, because of the positive change in temperature, the steel is exerting a compressive force in brass. Okay, but the other case, if you will reduce the temperature, the steel will exert a tensile force on brass, because it will say to brass to come with it. Steel will reduce in length less, but brass will reduce in very high. Yeah. Yeah. So I hope you guys have understood the concepts. I'll come with much more problems on uh, thermal loading in the next class, and we'll solve some of the problems on with that, and we'll see how the effect of thermal loading will cause the change in like the introduction of the thermal stresses. Okay, and we'll see then the other concepts which will be taken up in this week. Okay, so we'll close this session. Okay. Okay. Yeah. Thank you all for joining. Thank you. Yeah. Thank you.